All right, in the last video we looked at the two primary types of discontinuities, removable and non-removable. And what we're going to do in this video is come up with a formal definition of continuity at a point. So we're going to make a set of conditions that need to be in place in order for a function to be continuous at a specific point. Up until this point, our definition of continuity for a function has been that if we can draw the function without picking up a pen, it is continuous. But we're going to make this a little bit more formal. So let's look at this graph of f of x and explore the idea of what it means for the function to be continuous at this point when x is equal to c. So the function is clearly continuous, and what we're going to do is make a list of three conditions or three true statements that are true about this function, and these are going to be the three things that build your definition of what it means to be continuous at a point. And again, this is going to be something, these three conditions that we're about to list off are things that you will need to memorize. So here we go. F of x is going to be continuous at the point C if and only if, first of all, f of c exists. It must exist. If it doesn't exist, then it can't be continuous at that point. So what this means in normal people language is that there is a closed dot. That's not normal people language. It means that there's a closed dot at the x value, c. So what we're saying is that we have an output value. This means that we have an output value somewhere. That is the very first condition. If that isn't in place, then it's not continuous. This is a picture of what it would look like for f of c to not exist. When you have an input value of c, the output value is not there. It is not defined. It does not exist. The second condition for continuity at point C is that the limit has to exist. Let's put some s's at the end of exists. So the limit as x approaches c of f of x exists. It has to exist. And remember, what does it mean for a limit to exist? It means simply that the limit from the left must equal the limit from the right. This is a picture of what it looks like for the limit as x approaches c of f of x to not exist. The limit from the left and the limit from the right are not the same. Or again, symbolically, the limit as x approaches f of x, the limit of f of x as x approaches c from the right is not the same as the limit of f of x as x approaches c from the left. So far we have two conditions. We need the point to exist, and we need the limit to exist. And the last thing that needs to happen are those two things have to be the same. The limit has to be the same as the point that is defined at C. So the last statement is that item 1 and item 2 must be equivalent. So the limit as x approaches c of f of x must be equal to f of c. If these three things are in place, then our function is continuous at point C. Again, I really want to emphasize that this is at a point, a specific point in time, that in this case we are calling C. So let's look at a few examples. Here's an AP question. The question is, why is f of x not continuous at C? Here's C. Why is f of x not continuous at C? The very first condition says that f of c exists. And if we look at this graph, f of c does not exist. And that is the reason that this thing is not continuous. We can't say because there's a vertical asymptote. That is a true statement, but the reason that the function is not continuous at c is because f of c fails to exist. We have to appeal to our definition of continuity that we have just created for ourselves, those three conditions. 3 conditions. So the answer to the question of why is f of x not continuous at c is because f of c does not exist. Condition 1. Here's another example. Here's c. The question is, why is f of x not continuous at x equals c? Graphically, we can look at this thing and we know that there's a gap, so that's why it's not continuous, but this answer is insufficient. This is not an adequate response to the question, why is f of x not continuous at c? Of course there's a gap, but why, based on our definition of continuity, is this thing discontinuous? So we march through our conditions. Condition 1, does f of c exist? You betcha. F of c does exist. It's right there. When you plug c in, your output value is 10. So condition 1 is in place. Moving on down the line, we need to verify that the limit exists at c. So let's look at what this is. The limit of f of x as x approaches c is equal to, what are we getting infinitely close to? Let's call that a height of, let's call that 3. This is equal to 3. So we've just verified that the condition 2 is in place. The limit does in fact exist. And it is condition 3 of our limit definition that the problem occurs in. F of c is not the same as the limit as x approaches c. These are not equivalent. And we can show that. We can show that 10 does not equal 3. And this is what we need to show. It's because of this condition that the limit is not, or that the function is not continuous when x is equal to c.